All right. So welcome back. Today we'll be starting chapter 16, which is the sort of apotheosis of this course. And so what is it about but these gadgets called vector fields? And so what is a vector field? Well, this is a function. Let's start with the plane, say, and at each point of the plane, this function will assign a vector that can sit down at that point in the plane. So think about maybe something like a map of sort of like wind that would tell you wind velocity or something like that. That's a vector field. I think if you're interested in electricity, there could be electric fields. These would also be vector fields, I think. Okay, so we note these by big F is the letter for vector field. But notice it's a function whose inputs are two variables and whose outputs will also be two-dimensional vectors, so there'll be two-component outputs as well. So we can write this like this. We can write big F of xy equals to this sort of vector brackets, right? Because we want to emphasize that the outputs are vectors. But the two components can be each scalar valued functions of two variables. So we'll write those as p of xy and q of xy. This is the first component of f of xy. This is the second component. So each of these are just scalar valued functions, but they could depend on both x and y. So in the notation that we learned earlier this semester, the function notation, we can write a vector field as a function, big F, from the plane back to the plane. So it gives these inputs are like points in the plane, x comma y, and these outputs we'll think of as two-dimensional vectors. But we can denote both of those collections of objects by r squared. Okay, and similarly, we could do this in dimension 3 as well. At each point of space, we can set down a three-dimensional vector field. So that would be a three-dimensional vector field as a result of that, putting at every point of space a three-component vector. And so the way that we write one of those is with just three scalar-valued component functions. We write those as p of xyz, q of xyz, and big R of xyz. Okay, so let's look at an example. Here's an example of a vector field in the plane. It's big F of xy equals to minus y in the first component and x in the second component. So let's do some computations. So let's evaluate f at a few places. So at the point 1, 0, the x-coordinate is 1, the y-coordinate is 0. So the output will be the vector whose y-component is, or sorry, whose x-component is negative 0, alias 0, and whose y-component is 1. Okay. At the point minus 1, 0, we'll have still the x component of the output will be 0 because the y component of the input was 0. And minus 1 will be the y component of the output. Okay, following this formula again, at the point 1, 1 in the plane, we'll get that the vector field outputs the vector whose first component is minus 1 now and whose second component is 1. And then at the point minus 1, minus 1, we get the vector field outputs the vector 1, minus 1. Okay, and then we've got a few more points here. At 0, 1, the vector field outputs the vector minus 1, 0. At 0, minus 1, the vector field outputs the vector 1, 0. And at minus 1, 1, the vector field outputs the vector minus 1, minus 1. And last but not least, at 1, minus 1, the vector field outputs the vector 1, 1. So maybe we should draw a few of these just to see what does this vector field look like. Because writing it out here and saying it out here might not be as instructive as just actually looking at it plotted in the plane. So I'll start with this first guy here, f of 1, 0. So at the point 1, 0 here in the plane, we will put down the vector 0, 1. That's a vector that goes 1 in the y direction and 0 in the x direction. Okay. then maybe the next one on the list, at -1, 0, that should be back here. The vector that gets put down there is the vector that goes 0 in the x direction and now -1 in the y direction. Okay. And then let's come back up to this corner here. This is the point 1, 1. We know we're supposed to put the vector that goes -1 in the x direction and 1 in the y direction. That looks like that. Okay. And at -1, -1, that's at this point down here, we put the vector down that goes 1 in the x direction and -1 in the y direction. So that is this vector here. Okay, let's keep going. So at the point 0, 1, that's this point right here in the plane, we're going to put down the vector that goes -1 in the x direction and 0 in the y direction. So let's see that one there. Beautiful. And at 0, -1 on sort of other side of the x-axis over here, we're going to put down the vector that goes +1 in the x direction and 0 in the y direction. And there that is. And last but not least, we have, oh no, we have two more here. At -1, 1, that is this point up here in this corner. We're going to put the vector that goes -1 in the x direction and -1 in the y direction. That is this vector here. And okay, our last one that we decided to plot here today is at the point 1, -1, that's down here in this corner. We're going to put the vector that goes +1 in the x direction and +1 in the y direction. And I believe that one is there. Okay, and so as you can see, there's, an infinite number of points in the plane, and so it would be too much to ask for us to plot all of the vectors from this vector field that are relevant. But we're starting to see some kind of general shape take place here, or take form here, just from plotting, say, what was this, 8 of them? Okay, but still, even that took quite a bit of time. So maybe we might see if we could use GeoGebra to help us out. And oh my gosh, we can. So let's do that. So I'm going to kick over here to GeoGebra. Oops, that's Zoom. Hold on. GeoGebra. Love it. Okay, so if you Google search for GeoGebra vector fields, that's what I did. We have this little kind of app here, I guess, that was made by Juan Carlos Ponce Campuzano. We must thank him for that, whoever he is. That's great. So I put our vector field here. The first component is -y, and the second component is x. And look at this shape that we have here. It's this we can change the density or something if we like. So I think what we'd shown in our picture on the slides was very low density. But you can up the density here to see the shape really start to take form. This vector field seems to have this kind of swirling notion. I think it's rather pretty. So it seems to be kind of like swirling around the origin or something. The vectors seem to be getting smaller and smaller. Let's see if we can move in further. Oh no, I don't know what that scale thing does. So I don't know if we can zoom on this or zoom in on this or what. Ooh, wow. Oh, right, zoom, that's an option. I just didn't see that. Okay. Okay, so let's zoom in further. It looks like the closer we get to 0, the smaller or the shorter and shorter the vectors get. So that should be not surprising, since as you get really close to the origin, -y and x both get really small. So it looks like what's the vector that's placed at the origin for this vector field? At 0, 0, we should just have the vector 0, 0. Oh, so that would be the 0 vector gets placed there. So that's why we're not seeing anything actually explicitly placed at the origin in this example. Okay, but this is a great example, and you can use this tool here for more fun as we go forward. So in the next video, we'll come back and talk about some more concepts related to vector fields. It's an important concept that we're going to meet, that we're going to have for probably the rest of the term on our hands. It's called being a conservative vector field. So stick around and we will see more on vector fields in the next part.